So that was real numbers. Let's look at a very special type of real number, that being the rational numbers. And a rational number is basically anything that can be written as a fraction, where the top and bottom are integers. Okay? It will turn out to be a terminating decimal if we were to write it as a decimal. So any terminating decimal, or I should actually say terminating or a repeating decimal. So it could be an infinite decimal, but if it is an infinite decimal, it's a repeating one like we just saw. So ones like pi, which, yes, it's an infinite decimal, but it doesn't repeat. So that's irrational. Irrational are more interesting. As I say, simple definition is any number that's not rational must be irrational. Hence the prefix means not, I guess. All right. They can be written as unique infinite decimals. Well, theoretically, obviously they can't be written as unique infinite decimals because it would be impossible to write an infinite decimal. You'd be there for a very long time. But theoretically, they could be written as a... So we can actually prove that the square root of 2 we don't know the answer to. We're going to prove it is irrational. And we're going to use a method which is known as proof by contradiction. So proof by contradiction is where you actually start off assuming the opposite is true. So I'm going to assume the square root of 2 is in fact a rational number. Now, if it is a rational number, then I know I can write it as a over b, where a and b are both integers, and I'm assuming this is in its lowest form, so there's no common divisor other than the number 1 between a and b. So they're integers with no common factors other than the trivial one of 1. Rearranging that, I get b times the square root of 2 is a. If I square both sides, I get 2b squared is a squared. So therefore, I now know a squared is divisible by 2. A squared is divisible by 2. However, any square that is divisible by 2 must be divisible by 4. Because if you were to break a square down to its prime factors, every factor would appear twice because it's a square. Because you're multiplying something by itself. So if 2 is a factor, then there must be another 2 in there to pair it up to make the square. Thus 4 must be a factor. So I now know a squared is divisible by 4. So 2b squared can be written as 4 times something where k is some whole number, some integer. Because we've just said that a squared, which is 2b squared, is divisible by 4. So b squared, therefore, is 2 times something. Well, that means a squared and b squared are both divisible by 2. And they have a common factor. But our initial statement was they have no common factor. So I'm now contradicting myself. By assuming they have no common factor, I've proven that they do have a common factor. Therefore, my original statement must be false. So we know they don't. That was our assumption. So therefore, the square root of 2 cannot be rational. If it's not rational, it is in fact an irrational number. So that's a proof by contradiction. So a little quick one there. Exercise 2b is on irrational numbers. Question 4 there, same idea, but prove the square root of 3 is irrational.